America, where a significant part of the population still does not have completed tertiary education. And this will lead later on in their life in wider inequalities because of missed opportunities, because of the lack of education they had before. But more than that, we also observe that even in more developed countries where most people can actually go to high school or even to college, the current learning system is not as optimized as it should be. And what I mean by that is that all of the learning abilities of each individual are not leveraged as it could be. And so our goal was to try to make this possible. So the first question we ask ourselves is, how do we learn as individuals? And as you might know, we all have our own learning preferences. So some people will prefer using images, drawing on a paper when they're learning because they have a visual learning style. Other people will listen to podcasts, record their voices in order to listen to them because they have an auditory learning style. Personally, when I'm trying to learn efficiently, I like to write down on paper, to speak loudly, because I'm both a kinesthetic and an oral learner. And so each individual will have like a distribution of learning preferences according to the different materials they're trying to learn. And so those are specificities of individual that could be leveraged in order to improve the educational delivery. Similarly, there is also cognitive skills. So the cognitive skills are those abilities of the brain to process information, to process knowledge, and to learn. And there are like more than thousands of different cognitive skills, and each individual will be better at some cognitive skills and less good at other one. And so according to the way you will show an information or to the way you will ask a question, some individual will better process the information and better integrate the information you try to convey. So for instance, among the different cognitive skills, you could have flexible memory, which is the ability to unlearn information and relearn new information. You have attention, which is the ability to focus during an extended period of time on a specific subject. Verbal reasoning is more the ability to understand abstract concepts that are expressed in words. And spatial perception would be the ability to really understand concepts that are expressed in 3D representation and understand the spatial relation between different objects. And so our idea in scikit-learn was how could we leverage this information, this knowledge of individual about the learning preferences, the cognitive skills, the knowledge of different academic subjects, and maybe even their personality, in order to provide some tool that would help them learn more efficiently and more easily. And so our concept is pretty straightforward. It's to build some customized tests on different academic subjects. Each of those tests is going to be clusterized by the cognitive skills required to answer the question, and we will make different versions of the test regarding the different learning preferences of each individual. And so we will use these tests and give them to students and build profiling of each student using those tests. So profiling will give information about knowledge of different academic subjects. So if student is like early in his education, he will have basic knowledge of some subjects and maybe no knowledge of the other one. But for more advanced learners, we will have information about more advanced subjects they will know, they would prefer learning. But in addition to that, we also want to have information about how the brain works and how they prefer integrate new information in order to try better relevant material for them. And so the idea of the solution is to leverage this profile in order to web scrape the web and find relevant learning material online and recommend this learning material to the students so they can learn more efficiently. So this is the architecture of our solution, which is pretty straightforward. So we have this user database where we're going to store all the information about the users, and we have a large question bank. So in our study, it was mainly question about science, but the idea of the project is to make an education tool where students could learn about any subject they want to. So we have a large question bank, and one of the first analyses was to make sense and extract meaning of those questions. So we had to cluster questions according to the cognitive skills, the academic subject, and also see if we can have different versions for learning preferences. Then, using this question, we're going to provide interactive tests for students so they can interact in our app with our question, and we could learn from them what are the learning abilities and what are the different knowledge. And so all those information are stored in the user database. And the information of this user database are then again used by machine learning techniques and clustering in order to make some cluster of different students. So clusters that are based by the knowledge of academic subject, but also by brain differences. So those information we've extracted from our clustering are then used by our web scraping. So the first version of our web scraping was pretty simple. We used Wikipedia API in order to find relevant Wikipedia article, so mainly focused on finding the really relevant academic subjects they want to learn. But then building on that, we build more complex web scraping model, looking for other websites online, so academia.com, edX, different MOOC platform, and finding really relevant content that also try to find learning materials that will focus on the brain abilities of the particular student. But in addition to that, we also wanted to make a tool that could be used by educators. So this could be for current educators if the student is currently attending high school or university, or maybe future educators if the student is currently isolated from education. And this dashboard will provide a lot of statistics about students, statistics about past evolution, statistics about his learning preferences, and about the different performance he has on tests, about different academic subjects. So it could also be leveraged by educators to customize their education and their content to the different students. So in order to dive a little bit more on the pre-analysis we made of the question bank, we had like hundreds of thousands of questions, and we want to make sense of it. So in order to do that, we used bag of concept representation. So this is an improvement of bag of words which use work-to-vec representation, and basically we are building a clustering of different work-to-vec representation using spherical k-means, so k-mean with cosine similarity distances. And with those clusters, so each cluster represents one concept, and we're building document vectors that count each concept that appear in the document. So the document is basically the question, the abstract of the question on the solution, so we can like make sense of what was the question about. And along with a customized name entity recognition model, we build this clustering of academic subjects. So we have here the visualization of the latent space of the features that is colorized by cluster. So you can easily visualize that some clusters are really different from other ones, while others are more hierarchically clusterized. And this was used along with the elbow method to find the optimal number of clusters to make clustering. And if you extract the top relevant frequent word out of this cluster, it's pretty easy to like determine what a given cluster is about. So here you have like electrical science, life science, or marine biology. And in addition to that, as I mentioned before, we also clusterize our data set by the cognitive skills. So this was by using the name entity recognition model that we customized by adding some labels that are really created in order to recognize some cognitive skills. So for instance, comparison, abstract reasoning, geometry, geography. So all those new labels were added in our model. And then in a semi-supervised way, we clusterize the data set. So unlabeling a couple of hundred of data and running some classification model in order to label all of the remaining data set. And so we had like one encoding for each relevant cognitive skills for a given academic subject. So this was our tool. And once we built that, we wanted to assess how well we can do into transmitting knowledge to students and how they could learn new skills. So a question we asked ourselves was, what skills we want students to learn while using this app? And we reflected on what skills are important today in order to succeed. And we come up with 4 main skills, main one being creativity, so the ability to think out of the box and come up with original answer to question. Then cooperation, are students cooperating with other students on the app? And does they learn from one another? And interest was more, can we convey the taste of learning to students? So does they want to spend a lot of time on the app to explore new subjects? And finally, performances is basically how students are improving on the academic subject they are studying. So are they able to get better, which is basically the end goal of the app. So in order to track student success, we build interactive dashboard where you can plot a time series for each one of the metrics that I just mentioned. And in order to make things even more simple for educators to track student success, we just computed an overall score, which is basically a weighted sum of the different metrics. So you're going to choose different weights according to the importance of the metrics. So here it's like a baseline using cooperation, creativity, and performance. But you can like improve it with other metrics that you're going to try to measure on the use of the student on the app. And so as I mentioned, we have 2 user interfaces. So the first one is for students. We choose a mobile platform because nowadays mobiles are more and more widely used, even in underdeveloped countries, because they become cheaper. And in order to impact more and more people, it actually made sense to use mobile platform. And on the other hand, we build a web platform for educators to access different statistics on students. So you can see it on the right, where you can see evolution by academic subject and see statistics about time spent on the app, cognitive skills, learning preferences, and how many tests students have used and during all the history of the student on the application. So this is our team. So it is mainly composed of graduate students from UC Berkeley, but we were helped by mentors from AI for Good Foundation, so Jem Hodson, the CEO of the foundation, and Aljas Commerce, that helped us and gave us ideas about how to make it more efficient and our different machine learning and artificial intelligence techniques. So this is for my presentation, and I think I have a couple of minutes to answer questions if there are some.
So I was wondering about your question bank and sort of what sort of questions you have in there and how you grade them, because it seems like a lot of question banks I've seen are very factual questions, but it looks like you're trying to measure more sort of abstract things like creativity and sort of things that would be more conducive to open-ended questions that are hard to automatically grade.
Yeah, true. At the beginning of the project, we mainly have like a large question base of science questions, but about like any science subject, so biology, physics, math, and so we have a question base where we have a question, abstract about the question, solution. And so some questions are pretty large, like you can have like a couple of hundred of characters. And so we used, as I mentioned, name and entity recognition in order to find out more abstract things about the question. So we clusterize questions about different cognitive skills. So for instance, is a question require some spatial reasoning, some abstract thinking, or some calculus? So we try to find out what are the relevant cognitive skills that will require, that the student will need in order to answer the question. And so on the science question, like we selected, I think, 7 cognitive skills that were relevant for this question. And we build one-hot encoding for each question. Regarding some question will require maybe 2 or 3 cognitive skills. And we try to find out using key words or key concepts. So comparison, it could be like geometric form, it could be like shape, like different indices that could give us information about the abstract concepts that are behind the question. About creativity, on the science questions were not our main focus, but for some questions that require actually to write down long answers, this was more about questions that are tagged as being require creativity. And so in order to estimate the creativity of the student, it's more an analysis of the question, of the response of the student, and it's also more analyzing of the concept that the student raised and the similarity with concepts that are close to what the question and the typical answer we expect from the question are. So it's not currently all well optimized because we were really focused on science question, but we like explore more the analysis of response of students, and it was basically computing similarities between the response of the students and the expected response, and try to find out how creative a response can be from a student. Yeah.
So how would you distinguish a creative answer from a wrong answer? Like if someone's wrong in a really creative way, for instance.
Yeah, and that's a good question because that's pretty tricky. So I mean, it really depends on the question you're asking, you know, because it can be a question about philosophy, which is pretty abstract. So you need to first gather information about what you expect from the answer. But I do believe that for certain questions, it's really difficult to automate everything about differentiation between wrong answers and creative answers that is different, because I mean the AI cannot really learn what will be really creative answers that is completely different from what you're expecting, but actually is relevant because a student is pretty creative and has a good idea about something. So we hadn't found really solution about those really creative answers, but our current solution was more gathering information about what we expect from the solution and try to compute similarities between that. So there is like, if this is in the space of the solution we are expecting, we will consider it as good answers. And if it's far from the center of the space, we will consider it more creative. But it's not an optimal solution because, as you mentioned it well, some really creative answers and some question about some more abstract subject will require a human supervision in order to assess those things. And I do believe that to make an app that is really optimal in that way, we will also need some human power in order to supervise all of that, and maybe afterward try to improve the AI behind that. But yeah, definitely that's what we did.
Thank you.
Thank you.
Our next speaker is Sharon D. from Columbia University. She's going to talk to us about a reinforcement learning-based approach that she and her research group has implemented for autonomous vehicle driving at Columbia University. Please welcome Sharon D.
Thanks. Good morning. Okay. I'm Sharon D. from Columbia University. Today, what I'm going to talk about is how we apply the AI techniques for the self-driving car test when the self-driving car will interact with human-driven vehicles on road for the next decades, probably during this transition period. So the self-driving car I'm talking about is a level 5 driving car. So basically, you don't have to engage any human beings, so they can just sit in the car and let the car drive by themselves. So that's what Waymo is currently doing, and some other car companies are also testing their level 5 self-driving cars. However, there's some issue with this. Sorry, would you mind click this play button for me? Because this is a video. So in this video, I will show you. So probably it cannot be played. So there should be a play button on the bottom. Okay, I don't know whether it works. So I can explain to you. So in this video, basically I think if you are from California or Arizona, probably always encounter these Waymo cars. And then one person who's driving on the highway, and his webcam captured how this Waymo car tried to merge onto the highway. But the car who's videoing the Waymo actually was able to merge in. But then the Waymo actually attempted several times, but failed. And then it has to get off the highway from the next exit. Oh, okay, here you go. Great, thanks. So you can see it shows its indicator. And all the human-driven cars are able to merge in or merge out. Yeah, we can't even see the car because this driver successfully merged in. And actually, he has to go down from that exit. So what I'm gonna to say is when this self-driving car will interact with human-driven vehicle. So it's very crucial to first understand how human drives. However, this is how human driver behave on roads. So it's very dynamic and stochastic. So a lot of uncertainty happens. And from a traffic flow perspective, usually we'll plot a figure like this called a fundamental diagram. So the x-axis is the traffic density, and the y-axis is the traffic flow. Basic traffic flow means you stand at one point and you count how many cars passing by for a unit period of time. And then you will find out that as the density goes up, the flow first goes up and then goes down. So when density is really high, that's when the traffic jam happens. So in that right-hand side period, the regime, I don't know whether it works. So then actually human behave highly emergent. So there's this emergent behavior happens from this nonlinear dynamic. So during this time period, the traffic jam, the dynamic is unstable and there's hysteresis happen. So it's very hard to actually calibrate or propose a model to calibrate human drivers. Because there are this so-called free flow and traffic jam regime. So now we only give a very rough classification. So the free flow is the 2 dashed line on the bottom. So basically, they are driving at the maximum speed. The red one is the leader, the blue one is the follower. So basically, the follower and leader keep a certain distance, and then they don't have to decelerate or accelerate. They just drive at a constant speed. But the upper 2 lines indicate the traffic jam, how the trajectory behaves in the traffic jam. So you can see the leader car first decelerate and then accelerate. So that actually impacted the driver behind, and he had to also do the similar thing. So we found out this traffic regime actually heavily influenced the performance of a human driving model. Basically, if we use a driving model calibrated by one type of traffic regime, then that may not perform well for another traffic regime. Especially if here we show that if the blue line is the training curve, so if we use the traffic jam trajectories which experience the traffic jam to calibrate a car following model. So car following here, I mean when you are driving in the same lane and you are following a car in front of you. And then we want to use this model to predict the free flow. You can see that actually there's very high error, prediction error for that. But if we can select both traffic jam and free flow for the training data set, then the predictive power will be also enhanced. So this gave us a simple message. So we need to strategically select a training data set and a validation data set so that we can train a robust human driving model. So that's the goal of this study. So we want to train a human driver model so that we can design an optimal autonomous driving controller so that this self-driving car can cope with the dynamic and unstable human behavior. And then in this experiment design framework, we have 3 components: training data, validation data, and a modeler. So basically, we treat each of them as an agent or player. So then they basically play a game. So I will explain what's this. First, I will talk about what is modeler means here. This will come to so-called car following modeling framework that have been developed and used widely in transportation community. So basically, the black car is following a white car, and then we know its speed and position is V and X, and then we know the leader's speed and position. So basically, when the black car drives, usually it will use the information about what's the speed difference between my car and the leader car, and also the space highway. So how far I'm from the leader, and also my current speed. So using these 3 quantities, we can develop some models to predict what is the current, what's the acceleration rate I should use at this time point. And this mapping can be a functional form, which we call it a parametric model. So there are a lot of car following models proposed in this area, and usually it's come with ordinary differential equations. And there's also non-parametric models, so that becomes more and more popular. For example, people use neural network to represent how like this complex driving behavior when humans receive these input signals and how they behave, adjust their acceleration. So in our experiment design, we will use the non-parametric model, which is the neural network. So this is our methodology framework. So we have a 2-player game. The one player is the training data generator or selector. The other is validation data selector. So the training data selector, given we will give them a fixed data pool, and the training data select which data trajectory I want to use as the training data set. And the validation will do the similar thing. They will choose which trajectory I use to validate the model. And then but they have different goals. So the training data want to improve the prediction power of the model, while the validation data want to do the opposite. They want to reduce this prediction power of the model. So, and the reward they get is a delayed reward. So they don't get, so for example, we have 10 trajectories. I can give you this flow. Essentially, it's a combinatorial problem. So trainer, we use T to represent here, and the validator, we use V. So they have to select among these 10 trajectories, which one I need to select into my set. And then because it's combinatorial, so it's hard to enumerate every action. So we basically reformulate as a sequence of actions. So they will first look at the first trajectory and decide whether I pick it or not. Then they move to the next one. But this trainer and the validator, they play game alternatively. So it's like two players play chess or Go. So that's why we use the framework of AlphaGo here. And then they won't get it until when they decide pick every trajectory. They make the decision on every trajectory for that entire data pool. And the reward can be either the trainer win or validator win, or they have a tie. That depends on how much score they got. And the score depends on the prediction power of the model and also the number of data they select, because we assume when we generate one trajectory, it has some cost. Because in transportation area, when you do some experiment, usually it had to be natural experiment, so it can be very costly. So that's why we also add this cost of data selection into the score. And then that will give us a reward. So then this is one epoch. So then we do it again and again until it reaches an equilibrium. So at the equilibrium, the trainer cannot change their data selection to improve the model's predictive power, while validator cannot reduce the model, cannot further reduce the model predictive power by switching their data selection strategy. We also apply this to a public data set called Next Generation Simulation Data Set, or NGSIM. So this is a widely used public data set. It basically, how they collect data, they put a camera on a tall building next to a highway in California. So then the camera can record like 15 minutes of the traffic conditions, and then they use image processing to extract each trajectories. I think each trajectory is composed of the GPS points for every 0.5 seconds. So it's pretty high resolution. And then we select 10 trajectory as a training data pool, and each lasts for 10 to 20 seconds. It has both free flow and also the congestion regime. And for test data, we use, so basically the 10 trajectory is used for both training and validation data. And then we use a third data set, which is test data. It's one trajectory, but it contains like 50 seconds trajectory, and with both free flow and jam regime. So these two figures show the trajectory of that test data set. And then you can see on the bottom left graph, we show how our model worked. So we have a relatively low training loss as the training epoch grows. And then at the same time, we have relatively low prediction mean square error. However, on the bottom right figure, you can see if you don't strategically select the data sets, then it has very low training loss, but then it actually overfit the model. So it doesn't perform well on the test data set. So this framework is for calibration of the human driver data. However, it can also be transferred to for the future self-driving car safety evaluation. So we know that Waymo already hit this 10 million miles in probably last year. However, some studies show that if you really want to prove self-driving car is safer than human-driven car, you need, if you have 100 fleets and it runs continuously 24 hours, guess how many years it needs? Just say some number. Any idea?
1,000.
It's not that much, but 400 years. So basically, even the 10 million is not enough to validate a self-driving car. So that's why this is when the self-driving car will have to interact with the human-driven car for a long time period. That's why I think this is important for AI, some AI knowledge to apply to this kind of experiment design to test the self-driving car algorithm, not only on field, and it's also important to use some like this AI techniques. This is my team. So basically, my collaborator from applied math, computer science, and also law, we try to see how we can integrate unlinked engineering models with economic models of liability, so that we can infer some policy for this self-driving car regulation. So that's all about my talk. Thank you very much. Any questions?
Thank you for your talk. It was very interesting. I was just wondering, how many trajectories do you estimate you would need to train a model for every driving kind of environment?
So here we only use 10. 10 actually, eventually we select only like 5 or 6. Mm-hmm. We didn't select them all. But I think we definitely need more for the training. But for 10, I think now we see the model perform okay. So, but I can imagine if we include more and more data, it should be also fine.
So is that making predictions on just one piece of road? So when you're testing it, the performance of your model, is it on the same section of road that you're training your model?
No, we have a third independent data set. We call it test data.
Okay.
Yeah, so that's where but we use only one long trajectory. That trajectory has the free flow and also the traffic jam, stop and go.
Okay, cool.
Yeah.
Thanks.
Thank you. Okay. Thank you.
Thank you, Sharon. Yep. Thank you, Sharon. Next up, we're going to have a talk about mitigating demographic biases in social media-based recommender systems by James Folds and colleagues from the University of Maryland.
Thank you, Sarah. It's a pleasure to be here. Is this microphone on? Can you guys hear me? Yeah. Great. All right. So this is joint work with my students from UMBC, Rashid, Islam, and Kamrun Kia. It's really their work, so give all the credit to them. It's also joint work with my colleague, Dr. Jimei Pan. So we're interested in mitigating bias in social media recommender systems. So let me just talk a little bit about bias and where that comes from. So there's increasing awareness that there's bias in AI systems, and we need to address it. So here's a couple of examples. So in the top left, we have cases where Barack Obama was predicted to be playing basketball when he's playing actually football. And another picture, Chinese President Xi Jinping is predicted to be playing ping pong when there's no ping pong ball in sight. Other even more offensive cases, here's some pictures from Google Photos. They were automatically tagged pictures with black people, and then were tagged as having gorillas in that photo. And this can not only be offensive, but can actually harm your life. In the bottom left, we have a case here where there is a sentiment analysis classifier trained on text data. And when you give it stereotypical names from different groups, like white people versus black people, you find that the white names are given a positive sentiment, and the black names are given on average a negative sentiment. And so this could affect something like a system to analyze a CV to decide whether or not you should get a job. So if it sees your name, it could say, well, you're a good person or you're a bad person, therefore maybe you should get the job or not. And indeed, this is what happens. And so Amazon built this internal recruiting tool that looked at people's CVs and tried to decide who they should hire or not. But this is trained on the hiring practices that already exist, which are, of course, biased. And so they found that their AI system for analyzing CVs was biased against women. And so that could really affect somebody's entire career if they didn't get a job that they should have gotten. It also harms Amazon because maybe they didn't hire somebody that they should have hired. So that's a big problem. There's even more serious cases of bias. For example, in the criminal justice system, there's this tool called Compass, which is used for bail and sentencing decisions across the United States. And that was found in an expose by ProPublica to be biased against African Americans. And so it was twice as likely to predict that an African American would reoffend and commit another crime when they actually wouldn't, compared to a white person. Right, so these are serious problems. We want to try to deal with them, and today we're going to focus on recommender systems based on social media. And so one motivating application for this actually came up in the first talk by Kathy Matisse. So she was talking about the leaky pipeline in STEM and how women often don't end up in leadership positions and don't end up in high-paying careers. So there's the potential for recommender systems to affect that, especially when they're used for career advice. So we'll see a little more about that soon. So where does bias in data come from? There's lots of ways that your bias in data can arise and end up in your algorithms. One is that data often encodes societal biases. So if you train your model on social media data, which is data written and created by people, and those people are biased, they may be sexist or racist and other things, that can then be encoded into your model. Data is also going to typically contain the effects of inequity in society, so systems of oppression that hold some groups down and lift up other groups. Things like college admissions, entire society makes it easier for some people to go to college than others. And same with the criminal justice system. Some groups are more likely to end up in jail. African Americans are more likely to be charged with drug offenses than white people, even though they use about the same amount of drugs. We also often have less data for minority groups, and so that can harm performance for those groups. There was a study by Joy Uolamani and colleagues where they looked at computer vision prediction performance, and they found that because the data sets were imbalanced according to minority groups, and especially at the intersection of skin color and gender, then that caused inequitable performance for those groups. You can also get unwanted bias from the collection process. How did you get the data? And this can come up in very sneaky ways, potentially, which you might not even think about. So, for example, if you collect data from a smartphone app, then already you have a bias because you're only collecting data on people who have smartphones. And so you may not get any data from, let's say, poor people who don't have smartphones. You can also get bias from proxy variables. So you don't even have to include these sensitive protected attributes in your system for the bias to occur, because everything else is correlated with those variables. So in the United States, due to historical segregation policies, zip code is highly correlated with race. So if I take out my race attribute and I give it a zip code attribute, then I'm still going to effectively be predicting on something very similar to race. Same with things like education level and so on. All right. So we're going to focus today on social media-based recommender systems. So there's been some work already on recommender systems, but the previous work hasn't focused on fairness in social media-based recommender systems specifically. So that's what we'll focus on today. All right, so why are we doing that? So social media is a large source of data, which is then used to make decisions about us, and those decisions are often made using recommender systems. So we believe this is important. So we'll look at social media-based recommender systems. We have a couple of fundamental questions, which are, do different demographic groups experience mistreatment in the form of bias from recommender systems trained on social media or online social networks? And if so, how can we detect, quantify, and mitigate these biases? So these are our contributions. So we study fairness in that setting. We do demonstrate that this bias exists, can encode harmful stereotypes, and it can impact consequential decisions, like whether you're recommended to study a certain academic concentration. All right, and then we will develop a very simple technique to mitigate the bias. And we show that this actually works pretty well. It takes out a lot of the bias without harming accuracy too much of the overall system. So our data that we use is from Facebook social network. So the data was collected actually in a very similar way to the data that was in the Cambridge Analytica scandal. But I promise it's all above board. They used the opt-in consent for using the data for research. It was not shared, to my knowledge, with any conservative think tanks.